Welcome to free energy. We've already learned about some thermodynamic concepts involving entropy, energy, heat, and work. So now let's talk about free energy, or Gibbs free energy. So for a spontaneous reaction, the entropy of the universe has to increase. And reactions with large negative delta H values, large negative enthalpies, tend to be spontaneous. So remember, enthalpy is related to how much heat there is transferred. So a large negative enthalpy means that we have a lot of heat that's being released from our system. So if heat is being released from our system, then in general we say that exothermic processes tend to be spontaneous. So how can we use delta S and delta H to predict whether a reaction will or will not be spontaneous? And here we get to the Gibbs free energy. So, or free energy, sometimes it's called. So Gibbs free energy is called or symbolized with a capital G. And the Gibbs energy is equal to the enthalpy minus the temperature times the entropy. So G is equal to H minus Ts. Free energy, Gibbs energy, is a state function. Enthalpy is a state function. Entropy and temperature are also state functions. So everything involved here is a state function. None of them are path functions. So for a process occurring at constant temperature, then we can say that the delta G is equal to delta H minus T delta S. And now remember that the entropy change for the universe, delta S, is equal to the entropy change of our system plus the entropy change of our surroundings. And the entropy change of the surroundings is equal to minus delta H for the system divided by temperature. Which means that now we can say that minus T delta S for the universe is equal to delta H of our system minus T delta S of our system. The sign of delta G is very important in predicting the spontaneity of the reaction. If delta G is less than 0, then the forward reaction is spontaneous. So if delta G is negative, if the Gibbs energy is negative, then energy is being released. And if energy is being released, then the reaction is spontaneous. If delta G is equal to 0, then the reaction is at equilibrium and no further reaction will occur. Now that doesn't necessarily mean that the molecules or atoms involved aren't moving back and forth, but it means that there's no net reaction occurring. So every time A goes to B, B goes to A, on average. On the other hand, if delta G is positive, this means that the forward reaction is not spontaneous. It is in fact non-spontaneous, and that means that the reverse reaction is spontaneous, because the reverse reaction will have a delta G that is less than 0. So if delta G is greater than 0, then work has to be supplied from the surroundings to drive the reaction forward. We can still get that reaction to go, but we have to push it using some energy from the surroundings. So that equilibrium position in a spontaneous process is given by the minimum free energy available to the system. That point at which delta G is equal to 0. So the free energy decreases until it reaches this minimum value, and then nothing else happens because now we're at the minimum value. And going anywhere from there would increase would require a delta G that was positive. So we can then tabulate standard free energies of formation. So delta G F naught, and standard states are pure solid, pure liquid, 1 atmosphere for a gas, 1 molar concentration for a solution, and delta G naught equal to 0 for the elements. We can then, or we most often use 25 degrees C as the temperature involved here for our standard states, although we don't have to use 25 degrees C. So the standard free energy change for a process is given by this reaction, or this equation. So we have delta G naught, so that's the standard free energy change, the standard Gibbs energy change, is equal to the sum of, over all the products, of the number of the stoichiometric coefficient n on the product times the standard energy of Gibbs energy of formation there, and minus then a similar sum over all of the reactants. So the quantity then, delta G naught here for some reaction, tells us whether a mixture of substances will spontaneously react to produce more reactants if delta G naught is greater than 0, or products if delta G naught is less than 0. So the sign of delta G then tells us whether or not the reaction is spontaneous. So here we're going to focus on delta G is equal to delta H minus T delta S. So if delta H is less than 0 and minus T delta S is less than 0, then delta G will always be less than 0, and this means that the reaction will be spontaneous always. If delta H is greater than 0 and T delta S is greater than 0, then delta G will always be greater than 0, and this means that the reaction will always be non-spontaneous. If, however, delta H and minus T delta S have different signs, then the sign of delta G will depend on the sign and magnitude of the other terms. So on delta H and T delta S, which means that temperature will be an important factor. That there will be some temperatures at which the process is non-spontaneous and some temperatures at which the process is spontaneous. And that means that if we're crossing over between spontaneous and non-spontaneous, then there's some temperature at which that process is reversible. It's at equilibrium. So let's look at some reaction, at this reaction, where we have solid water going to liquid water. In this case, the sign of delta H is positive, which means that we are putting in energy. Right? We're putting in heat, energy as heat in this process. But delta S is also positive, so entropy is going up as we move from a solid to a liquid phase. But we have to put in energy to get this to happen. So, if we have a temperature less than 0 degrees C, then the delta H is greater than T delta S, and delta G is greater than 0, which means the melting of ice is non-spontaneous when the temperature of ice is less than 0 degrees C at 1 atmosphere. Ice doesn't melt at less than 0 degrees C. But at a temperature greater than 0 degrees C, then delta H is less than T delta S, in which case delta G is less than 0. It's spontaneous, so the melting of ice is spontaneous when the temperature is greater than 0 degrees C. And at 0 degrees C, then delta H is equal to T delta S. And then delta G is equal to 0, which means ice and water can be in equilibrium at 0 degrees C and at no other temperature if the pressure is 1 atmosphere. So, even though a reaction has a negative delta G, it may occur too slowly to actually be observed. Which means that thermodynamics gives us the direction of a spontaneous process, but it does not tell us the rate of the process. That is the role of kinetics, not thermodynamics. So, that was free energy.